Okay, so first question, bit of revision on what we did last lesson. Proving that Boolean expressions are equivalent. Now we've had a look at how we would do that using a truth table. So if we have A and B there, 0, 0, 0, 1, 1, 0, 1, 1. And we then compute the values of whether it's 0, 1 based on all of these different expressions and operators. So here we have A or B, and here we have not A and not B, and then we've got to disjunct them using the disjunction symbol. This is going to be quite a lot of work to prove using the truth table that the left-hand side here is equivalent to the right-hand side. That's quite a lot of work. Luckily, our rules of Boolean algebra mean that we don't necessarily have to do a truth table each time to prove that the left-hand side is equal to the right-hand side. We just have to be really pedantic with the way we do this algebra. So I'm going to go from, we have to decide on if we're going to prove any kind of identity or anything involved in this, we've got to decide which way around we're going to do it. And I'm going to go from left to right here. So I'm going to start off with my left-hand side expression. So A and B, or not A and not B. Okay. Now, I know that when I conjunct, when I put and an or with a not A and an A, I know they're going to disappear using some of the rules. So I'm going to multiply this out as I would in normal algebra. So first of all, I'm going to have A or not A. Okay, so A or not A. Then I'm also going to have and A or not B. I'm also going to have B or not A. And finally, I'm going to have B or not B. Okay, now we're almost there. We know that A or not A is going to be 1, and B or not B is equal to 1. This is the complement rules. So it's quite easy to prove that. If we had A, we had not A, 0, 1, and 1, 0, A or not A, it's going to be 1, 1. That's always true. It's a tautology, the word which we use. Something which is always true, we call tautology. Anyway, so this becomes just 1, and as well as this becomes 1. So what we're left with is the stuff in the middle. So it's A or not B, and B or not A. Now you might think that we're done here because it looks very similar to that, but isn't quite the same way. Here we have an A or not B. We've got the A or not B first, and here we've got not A or B. Now, it's quite pedantic and quite finicky, but we can move these around as we see fit, because rules of these operators are what we call commutative, which is it doesn't matter which order we do these things. So not A or B, and let's get this right, A or not B. Okay, and we have the right-hand side as required. There are a number of different ways we could prove this. We could use a bit of De Morgan's rule on the left-hand side, because we know that A and B, or not A, right? Not A and not B. Okay. Now that's our left-hand side again. Now if we look at this expression here, we can almost factorize out the not symbol. This is what De Morgan's rule is. We can factorize out the not symbol, but then change that into an or. Okay, so we get A and B, or so this becomes not brackets A or B. Okay. That hasn't actually helped us that much, actually, come to think about it in hindsight, but it hasn't really helped us improve in that. But that is another rule which is useful, this De Morgan's rule, where factorising out and not. Okay. So that's quite a cold Boolean logic question, and how we'd prove it using the laws of Boolean algebra. What we're going to move on to next is switching circuits. Now, Boolean algebra is the perfect language to represent switches and light bulbs and how we would switch things on. A lot of our circuit boards in computers and anything digital, anything which is electronic, exploits Boolean algebra. The designers would exploit Boolean algebra in order to design circuits which achieve certain things. Now we're going to have a look at draw what we mean by these circuits. If we take a value of A and B, now we know that A can either be on or off, or B actually. Okay, and what we mean by on or off is that 0 represents a state of it being off, and 1 represents a state of it being on. And you can think of this very simply as a light bulb and a switch. Okay, so we have a switch here, and that's the switch A, and there's a light bulb there. At the moment, this state is representing not A because the switch is open. Obviously, if the switch was then closed, the light bulb would go on. Okay, so 0 represents the state of being off, the switch being off, and 1 represents the state of it being on. Okay, now we can begin to make lots of comparisons with circuits now, and these can be written circuits. Now we can write using Boolean algebra. So take for example this one. We've got A or B and A or C. Okay. Now what we're going to have, we've got three variables here. We've got A. Sorry. We've got A, B, and C. Now first of all, we want to represent A or B. Now that is done by having circuits in parallel. Okay, this is the switching circuit which represents A or B. Because if we have a light bulb here, and we don't usually draw the light bulb, but if we have a light bulb here, if A is on, then if we have a power pack here, we don't draw the power pack. There's our battery. I don't know if that's the proper physics way of doing it, but who cares? Represents the point. Here's the battery, and if the power was going through these wires, imagine these were copper conducting wires. If A is on, the light bulb goes on, or if B is on, the light bulb goes on. Okay, so A or B represents switches in parallel. Okay, we're going to get rid of the stupid lamp bulb on the battery pack. Now I've also got A or C. Now the trouble is here, we've already used A. So what I might be tempted to do is if I just move that down. Okay, this is again A or B. Okay, there's A or sorry, it's A or C. Now you're thinking to yourself, well, actually, I mean, how can we have a switch there? Now, the key is, although we're not too worried about how this works, it is possible to gang, what we call gang, the same switch together so it's replicated twice on the circuit. we're not too worried about how this works in practicalities, because this is maths we're talking about here. But it is possible to have the same switch twice in a circuit, and we call this ganging. We've ganged the switch A there, so it appears twice in the circuit. Now, here we've got the two separate Boolean expressions for OR. So the light bulb, if it was here, would switch on if A or C was on, and the light bulb here would switch on if A or B was switched on. These two have been combined together with an AND symbol, okay? And that means they get combined together. So, because they're AND, these switches have to be in series. Okay, these switches have to be in series. So although I've drawn the two expressions here for OR, what I need to be doing now is putting them in series. And I've lost a bit of my circuit there. Move that over there. Okay, let's get the circuit here. Okay, there we go. There it is. Nice and easy. Okay, so we've got two sets of switches on parallel. Now what that means is that our output here is going to be whatever the Boolean expression is for A or B and A or C. Okay, so that means that let's take a particular configuration of A, B, and C. So let's say that A is on, B is off, and C is on. Is the light at the end going to switch on? Okay. Well, it would go through here. This is fine, and it would go through here. So in this case, we have that the state is switched on. If, however, we make A A0 and B0 and C1, we can see here it stops here. It's not going to get through these gates because the switch for A and B has been switched off. So therefore, the final state here would be the lamp wouldn't be switched on. Okay. So that's what I mean by switching gates. Now, another way we can represent these in Boolean expressions in logic gates is a different type, but it's called combinatorial circuits. Now, you have to remember a few things here, but this is where base symbols represent different expressions. So, if we ignore the question for the minute, we have this symbol here. Okay. Now this represents not. Okay. So if we have a Boolean variable going through this gate, it will turn it into a not A. This is what we call a not gate. Okay. We also have an AND gate, and we have A and B going through an AND gate. Now, an AND gate is a straight line, kind of, probably a bit badly actually, because the way it's been calibrated the board. Okay, and that goes to A and B, is an AND gate. We also have, maybe, now, your gate is that's quite a nice one. I'm pleased with that. Usual, A or B. So they're the basic ones. Now we also have, as you may see as well, a NAND gate. This is basically a NOT gate plus an AND gate. Okay, so A and B would go there. Okay, and it's the same as an AND gate, except we've got a little circle bit there. Notice the circle bit from the NOT as well. And basically that goes to not A or AND B. Okay, so there are four basic combination logic gates. We call these the logic gates. Okay, so now we can draw these circuits using these gates instead, and we're after the circuit not A or B and A or not C. Okay. Now, if we draw in a switching circuit for this, Okay, let's do that, no problem. We're going to have to gang A because it appears twice. So this is A or B, so there's A. And there's the B there, that says A or B, or in fact it's not A, sorry. So it's not A or B, and then because we've got the AND there, it's going to be in series. So A, not C. Okay, very simple. That's the switching circuit for that. But we want to do the combination circuit for that using the Boolean expressions. Now, A appears twice here. Now, let's do the first one. Let's do the left-hand side. We'll start off with A. First of all, it has to go through a NOT gate. Okay, so first of all, it's going to be a NOT gate there. Okay. So it goes through a NOT gate, and out it comes, and it's not A. Now what I do is I write in pencil what the output is. Okay, so I know that's going to be not A. We've got a B here. Now it's not A or B, so they're going to connect into an OR gate. Okay, let's put something like that. Okay. And notice here that the variables do not appear on the wires, if you like. The combination circuits, they appear at the end, the beginning only. Okay, so here we've got not A and B. Now, let's look at the next one. Now we've got an A there, and we've got a not C. Now, really, we want to get a not A somewhere. I'll put the C down there. Now what I'm going to do is, I'm going to draw another wire coming from A. I'm going to pretend it jumps over B, so I'm just going to do that, and that's legitimate notation. And so there's the A, that's how we get the A, this bit. We want a not C, so C is going to go through a NOT gate, and then it's going to go round like that. So we've got a not C coming out there, and it's an OR gate. Quite enjoyable to draw, really, in a weird kind of way. Okay, there's an OR gate. So outside we do have the A or not C. Finally, these combined with an AND. Okay, so we can move these up like that. I'm not too worried about the straight lines here. It looks neater if they're straight, but who cares if it gets it right. There's the AND symbol, and that means that finally we have the output we're going to have is what we have. So not A or B and A or not C. Okay, so this represents the combinatorial circuit for this one here. Okay, so finally I'm just going to go over a quick exam question which takes into account all of this. Okay. And it explains it in terms of a real-life situation. So a machine has three components. Get rid of that. And that's the second. The machine has three components, A, B, and C, each of which is either active or inactive. Okay. The machine is active if A and B are both active. Now, right away, I'm writing these things in Boolean algebra, in Boolean logic. I'm not going to use capital A. I'm going to use little a and little b. Okay. So this represents, so we've got A and B, so we've got A and B there. Okay, that represents my Boolean expression there. The machine is also active if A is inactive. Now, A is inactive is saying that not A, and C is active, so and C. Okay? And it's also inactive if the machine is active if B is inactive, so that's not B, and C is inactive. And I just want to apologise because I've got my symbols all mixed up there. That's and C. Oh, sorry. A bit of a fiddle here. A and B, A and C, not B, and not C. Okay, there's my three expressions. Otherwise, the machine is inactive. Now, what we're saying is that the machine is active if this is true, or this is true, or this is true. So our machine basically is only active if this expression is active. So it's A and B, or not A and C, or not B and not C. Okay? If this is true, if this is represented by a Boolean expression 1, the machine is active. If it's inactive, it's represented by a false. Okay, and that's what it says in this sentence there. Okay, draw such a circuit. Now it isn't saying whether it's a combination circuit or a switching circuit, so we can choose either way here. I'm going to be more tempted to do combination circuits, but actually it doesn't matter either way here. Now notice that the AND symbols, if we do a switching circuit, the OR symbols represent things in parallel. So we've got two things in parallel, three things in parallel here. We've got this expression, that expression, and that expression are going to be in parallel. And I think this is probably going to be the nicest way to go through this. Okay, so we're going to have three branches, each representing, because we've got the ORs, they represent things in parallel. The AND represent things in series, so the first thing is going to be A and B. The second one is not A and C. Now A and not A have been ganged together. And the final one is not B and not C, and there's the output. Okay, really nice marks there. Really not that difficult either. If we want to do the combination, want to do the combination, again it's not going to be too bad here. So A, let's have an A, let's see how this works. So we've got an A and not A. They all appear twice, so it's going to be a bit messy, this circuit. So we just have to get our A's, B's and C's and just buy that out here. First of all of them are going to have to be knotted as well. But let's just deal with the first one. A and B there is going to be represented by this one. So there's A and B. Okay, that one's there. Let's sort out this one, not A and C. So I'm going to have to put it through there, jump it over. There's a not symbol, there's a little circle. So not A and C goes through like that. Not B and not C. Right, now this is where it's going to get messy. So, I'm just the doctor. Make the needle sharp. Right, so that's going to represent a not C coming out. And there's another one for not B. Okay, there's not B and not C. They're going to come out and they've got to go through an AND as well. Interestingly, this conjunction of that one, and that one, we could do this as a NOR gate, which is basically that. An OR gate with a NOT add-on. You might want to think about why that is, but it's not a problem, because I haven't actually talked about this symbol, that symbol yet. Think about what that is equivalent to in terms of De Morgan's rule. But anyway, we've got the three expressions out. This one here is going to give us, this one here is going to give us that expression. For this expression, it's there. And for this expression, it's there. And they're ORs. Now we can't put more than one in at a time. So I'm going to do that first. It doesn't, remember, it's commutative. It doesn't matter which order we do it in, and it's also associative. Okay, so we can do these two first. This is Boolean algebra, so we're going to do an OR for that. And then getting that out there, draw another OR there. Okay, and there's our final output, which is what we wanted. Okay, so what I'm going to ask you to do is, there's a number of questions which I'd like you to do from the book. I'd like you to have a look at page 120, exercise 4.